Welcome to Study Loop.
This is chapter 21, problem number 10. We have a loop of wire that is embedded in an external field whose direction is into the page. So this loop is actually circular. Let me use a different color for the loop. The loop is circular. However, the diameter of the circle is changing. Let me write down the magnitude of the magnetic field, 0.65 teslas. And the diameter of this loop of wire is changing from 20 centimeters, decreasing to 6 centimeters within a time interval of 0.5 seconds. So in part A, we're asked to show the direction of the induced current. Now, in order to figure out the direction of the induced current, we got to remember Lenz's law, right? Induced EMF equals to negative of rate of change of flux. So this negative sign here means whatever the change is to the magnetic flux, the loop itself is going to want to oppose to that change, right? So let's first figure out what's going on as far as the flux is concerned when we actually decrease the diameter. If we decrease the diameter, flux would be decreasing. Flux into the page would be decreasing, correct? Because the area is decreasing with respect to time. So if flux into the page is decreasing, then the loop itself is going to want to oppose to that change. So it's going to want to create the flux that is actually into the page, right? Because it was decreasing as you go into the page. So you want the induced flux to be into the page. For that to happen, the induced magnetic field by the loop has to be also into the page, right? Inside the loop, so that we can create a flux into the page to oppose to this decrease. So when that's the case, then from the right-hand rule, number 1, by aligning your thumb in the direction of this B induced and the rest of your fingers are curling around the circle, you can conclude that the induced current's direction has to be clockwise, right? From the right-hand rule, number 1, I induced has to be it's clockwise. Now, in part B, let's go to the new page. In part B, we are asked to calculate the magnitude of the EMF. So it's going to be delta phi over delta t, that equals to delta t b times A. In our case, B is constant, dA over dt, right? So dA, delta A means A final minus A initial. Final is pi d final over 2 squared minus initial is going to be pi d initial over 2 squared. As you can see, this is going to be a negative value. That's where we're going to take the absolute value if you're looking for the absolute value of the induced potential, right? So we can put everything back in this equation, right? B was 0.65 teslas, and delta A is going to be 3.14 for pi. D final, which is 6 times 10 to the power of negative 2 meters divided by half squared minus 314 pi 20 times 10 to the power of negative 2 over 2 squared, right? So let's put it in parentheses like this. And in denominator, we have delta t, which is 0.5 seconds. So then if we plug everything there in, we're again taking the absolute value of this term. So it's going to come out to be positive. Then what we find is 3.7 times 10 to the power of negative 2 volts for the induced EMF. And then in part C, we're asked to calculate what the induced current would be if the resistance is 2.5 ohms. As you know from Ohm's law, potential equals current times resistance. Then from here, we calculated our potential to be 3.7 times 10 to the power negative 2. In order to find the induced current, then we're going to do epsilon divided by R, 3.7 times 10 to the power negative 2 volts divided by 2.5 ohms. So this is going to be equal to 1.5 times 10 to the power negative 2 amps.